Hi, Year 12. Seeing as we are starting some new content that we've not studied in lessons before, I thought it might be helpful if I record a video on this topic, as trying to read it up yourselves I think would be very, very challenging. So I'm going to run through infrared, the basics of it, so what it's used for, how it works, and then how we interpret the spectra to identify molecules. So we've got infrared spectroscopy. So it's using infrared light. I'm sure you all know what that is. And so this is used to identify the functional groups in molecules. So we use it to identify functional groups. So infrared is useful for identifying if it's got say it's an alcohol, if it's a carbonyl, so it's got that CO double bond, if it's an alkene, whether it's got a CC double bond. Those are the kind of things that infrared can be used to identify. It's not very useful for finding the exact structure of a molecule. The next thing we'd be doing would be mass spectrometry. That is more useful to identify the actual structure of the molecule. And NMR, which you study in year 13, that is by far the most powerful technique for identifying the actual molecule. But infrared is is very useful. It's very frequently used by chemists, and it's much easier to interpret than the other ones are. And so it's a great place to start in terms of structural identification and spectroscopy. So we're going to look at how what's going on kind of under the hood, how it works. To start with, I think this is useful to help you understand what's going on. They're not going to actually ask you about this in the exam though. So the first thing is we just consider a simple chemical bond. We've got two atoms that are bonded together. Now this bond, which I'm going to represent, it's sort of like a spring. Now the bonds are not sticks that are rigid and hold the atoms together at exactly a fixed distance. If you've come across bond lengths before, we might say, well, the bond length is a certain number of nanometers between these two atoms. That's an average. It's actually vibrating back and forth. Just like if you took two balls, held them together by a spring, and they bounce back and forwards. Now we can change the amount of energy stored in that vibration. So there's the sort of resting energy where it is moving, but only moving a small amount. We might call that the lowest energy level. So if I plot a graph with energy on the y-axis, that would be what we might call the ground state. And then there are multiple different energy levels where it's vibrating more and more each time. And if the molecule is sitting on this position here, if it absorbs the right amount of energy from a photon of infrared light, it will jump up to that previous level. And so a photon that has this energy value, which for people studying physics, E equals hv, corresponds to the wavelength of light that it will absorb. And infrared spectroscopy is going to be measuring those wavelengths of light that are absorbed. And that makes the molecule vibrate with at a higher energy, so it'd be vibrating back and forth faster. An interesting point is that you can't actually remove all of the vibrational energy, so this value is not zero down the bottom. There's a small amount, and that's called the 0 point energy, which you sometimes see in pop culture used in a completely wrong way. So that's the basics of what's going on at the molecular level. Now, how the machine works. It is in the textbook, but I've never seen a question come up, which is just roughly how the machine is set up. So an infrared light source, which I'll just represent by this box here, is giving off waves of infrared light. And that's it's not all of one frequency. It's not like a laser that gives off all the same frequency or wavelength of light. It's a broad spectrum of infrared light, so a whole range of different wavelengths. We then put a sample. You don't need to know how the sample is set up, but the light is then going to travel through the sample, and some of the wavelengths are going to get absorbed and some of them are going to be transmitted. They'll pass through. So some, let's say this one here in the middle, doesn't go through, so that one gets absorbed by the sample, but the other ones can continue through, and then on the other side is a detector. and that just measures the intensity of light that comes through the sample that's transmitted at different wavelengths. So let's say this is a short wavelength infrared, full infrared. That's passed through, the detector will record that there's a high intensity of that slightly shorter wavelength infrared light. If this is the longer wavelength, the detector might also see that that is transmitted a bit better. And then let's say this middle of the road wavelength infrared light, that got absorbed, and so the detector won't detect as higher intensity of that infrared light. That's going to plot that onto a graph. So the way the graph looks, or the spectrum, the rough layout is we've got on the y-axis we have transmittance. Now transmittance is done as a percentage. That's just the percentage of light that passes through the sample. So if it's all absorbed, if all of that light is absorbed, then the percentage transmittance would be 0. It all got absorbed, so our graph will be right down the bottom. And then we have 100% transmittance, where all the light passes through as if there was nothing there. So if we didn't have a sample, if it was a blank run, we'd expect a line right across the top. So all of the light just passed through, and so the detector detects 100% transmittance, all the light passed through across all different wavelengths. So this, down the bottom, this is going to represent our wavelengths. So the frequency, or frequency wavelength, very highly interconnected. That's what's plotted along the x-axis. Now, those give rather inconvenient numbers. If we used frequency or if we used wavelength, we wouldn't get numbers that are easy to deal with. And so instead, chemists use this thing called a wave number. Now, you don't need to know how it is calculated. You don't really need to know anything about it other than it's what's plotted on the x-axis of the infrared spectra. Now, it's measured in inverse centimeters, very weird unit. It just relates to the wavelength of the light. So on the left side, which is where we have the high number wave numbers, it also runs back typically from 4,000 going down as you go right. So it's the opposite way around to a typical graph. This is the highest energy, highest frequency light, so shortest wavelength. And as we go to the right, we're getting lower energy, longer wavelength light. Now, for infrared, we're now going to take a look at how the key peak. So this is the way that you're going to be able to interpret infrared spectra effectively. If you look at the data table on the sheet that you get with your periodic table, you can see this huge long list of wave numbers corresponding to different functional groups. And so there's about 15 or something of them on there, and most of them are useless, and they just get in the way of you being able to effectively interpret infrared spectra. Realistically, you only need, say, about 4, maybe 5 things that you can identify from an infrared spectrum. And frankly, you shouldn't really need the data table at all. So if you're getting good at this, the data table is just there as a reference point for the numbers you're going to write down. You can fully interpret it without the use of the data table, and then you just refer to the data table to make sure you've got the right number to write down in exam questions when we get to that later. So what I see from students that are never doing well at infrared spectroscopy is they just hug that data table, they just look at that, they're just trying to match stuff up with the data table. That's how I was taught it when I was studying my A-levels, and I was rubbish at it. You need to do it without using the data table and learning those key peaks. So the key things we're going to be looking out for: we're going to be looking out for OH groups. So there are 2 types of OH group we're going to come across. There's alcoholic, and there are carboxylic acids. So they both have an OH group, but they show up very differently and very distinctly in infrared spectra. The other one is the carbonyl group. So the CO double bond. Very, very distinctive, one of the first things you should be looking for. The other one is a CC double bond. It's much more difficult to spot. It's much easier to overlook it, but if you do spot it, it's fairly obvious when it's there, and it tells you a huge amount of information. And really the last one is an NH2 group. It doesn't come up very often, but it's pretty obvious in the spectra if you see it there. So as I do not have the equipment to do sort of adding images into videos, I've just sketched out an example spectra. So this is a spectra of a molecule, and it's going to show us a couple of those key peaks that we want to look out for. It's not a perfect diagram, it's missing some of the detail, but I've got the things I need, we really want to highlight in this. I'm going to set you some work on the using the frog program, where you're going to see some much more detailed spectra, and I want you to go through and annotate them or assign the spectra in the way that I'm going to be doing here. So this one here, this is a good example of an alcoholic OH group.